Hello everybody. Sorry if my brain is a bit slow. Here is 4 a.m. something. So we are going to discuss about Omnitrace. It's I would say a new profiling tool. We'll say new, but now I think it's close to 1 year. Um, and many people contribute to the slides, and people who are not in this slide, but through further discussions. And we'll discuss about the profiling. We already discussed about the Rock Profiler. I suppose you saw some of this stuff, what the Rock Prof does and what can support and all of these functionalities that Rock Prof can handle. And then it's the Omnitrace. So the Omnitrace at one layer, it uses RockProf. It's not independent from RockProf, but it does comprehensive trace collection, CPU and GPU, and supports CPU copy, heap API, HSA, GPU kernels. You can see about OpenMP, OpenMP for CPU, MPI, Cocos, pthreads, multi-GPU, and trace can visualize with Perfetto. So basically the Omnitrace is about to see the timeline, to understand how my application behaves, iterations, and other stuff. While the next tool that we'll discuss tomorrow is about kernels. So the OmniPerf does an automated collection of hardware counters. So you give your application, and depending on what you declare, it runs for many times, collects counters, and it does analysis and gives you back information about speed of light, memory chart, roofline. Is my kernel memory bound, compute bound, or needs improvement, for example? Kernel comparison. And you can do visualization with Grafana or standalone GUI. And here you see just, I will not explain this now. It's a memory chart to see from each layer what's the request you do and the bytes and how many compute units you actually use, etc. So I wanted just to mention that OmniPerf uses also RockProf at one layer. And the difference between these two is the one is timeline and cares about the MPI, cares about communication, etc. And the other is like, I don't care about communication, I care only for the kernel, and OmniPerf needs to run the application with only one MPI process. So you cannot run with two MPI processes or more, because actually it does something like replay on RockProf, and RockProf doesn't support yet about MPI processes to replay. So you need to have a program size that you can run with one MPI process, and you give that to OmniPerf. Now, I think maybe you saw that already. So where should I focus? So I have an objective, right? Where should I focus my time? So if it's about where, you need timeline, traces, profiles, and causal profiles. And how well I'm using the GPU, you can use also from the timeline, but also you need roofline. And the way I'm seeing this performance, you need hardware counters to understand what is low or it's enough to see, I don't know, the cache hit rate and other stuff. And before we had the RockProf for everything, right? And RockProf was not really providing the best for the best. And so it did the extra more work about this. And then we said, okay, let's do the Omnitrace to handle the timeline and the hardware counters, and OmniPerf for roofline and hardware counters. Now, both of them use hardware counters a bit different, and we will explain that. So let's talk about Omnitrace. It is open source, it's available here. Okay, it's not part of RockM stack, neither Omnitrace, neither OmniPerf. They are research tools. They support C, C++, Fortran, Python, OpenCL. They do dynamic segmentation, statistical process sampling, and causal profiling. Now, I want to mention, because we don't present here yet, causal profiling is something really new. What is that? This is about I have a code, let's say in CPU, and if I take this function and improve it by 20% on the GPU, what would be my outcome? So causal profiling can give you feedback. If you improve this code, what would be the gain of the performance? It's really good functionality. It's really new, and soon we'll have a material to present. Data analysis, high-level summary, comprehensive trace, critical trace analysis. The critical trace analysis are connected with the causal profiling. And parallelism, as I said, MPI, OpenMP, pthreads, heap, HSA, Cocos. For example, for Cocos, I was in a hackathon a few months ago, and two people had Cocos, and they said, I don't know how to visualize, and I said, let's try it. And so I just used it with Cocos and just worked directly. It was my first time using the tools with Cocos, and they were really working. GPU metrics, hardware counters, HSA API, heap API, heap trace, HSA trace, memory, and thermal. But you can have also CPU metrics, okay? The hardware counters, which is the classic one from PAPI, timing metrics, memory access, network I/O, etc. Now, there is documentation. It's really updated, and you can find a lot of information there. So installation, if required, it's extremely easy. I mean, we had some difficulties, and I will explain. So you say that I want the latest Omnitrace version, which ROCm version I have now installed, where I want to install it, and wget with these options. You see here the parameters here, the Omnitrace version, okay, and also you say install. And based on the ROCm version, so it identifies automatically which version to install. I have to say that I mean, because we had access to the system for not a long time, and we had problems to use the Omnitrace, so we installed another version based on 5.02 because I think the ROCm version 5.43 on the system is not is a custom installation and has some issues this moment. Now, and you can set up the environment like that, but you have also the modules. It's already in the HackMD, not a module, but you can load the module from the custom path. Needs no root access. Anybody can install its own version. You can install your latest version in your project if you want something from the latest version. It's not public available, etc. But I suppose the support team will provide the latest versions when they're out. Now, instrumentation modes. Dynamic binary instrumentation characterize performance, a sample, every invocation, and large overheads, okay? So I will show you that when you do dynamic, it goes to instrument any dependency and any library. So it can be like a lot of overhead to take the trace. Now there is sampling, that's periodic sampling of entire application, statistical and process sampling. Again, does some sampling. Personally, because for me there are different concepts of sampling. Just generic sampling, I'm not also a fan of it. I want to know every event, what happens. And now the basic command line is Omnitrace, and I will show you more. Omnitrace option dash, and this is your application, your binary and arguments. In order to take help, omnitrace.h, okay? And when we say some commands, it's not necessary, but you need to do srun, right? And depending on the command, you don't need srun or you need srun, and it's like that. So don't forget Omnitrace options, dash, and then your application. And we decided the dash to be for both Omnitrace and Omniperf, so to be something like similar behavior and to remember when you use the tools. Now, for any problems, create an issue here. It's really responsive, of course, depending on the issue, right, and the request. If it's a really huge request, it can take some time. I mean, for us, for something critical, can be fixed 24, 48 hours, but again, depends how much development it needs. And here's the documentation that it's really extensive, I believe, so it's quite good. Now, if I can say, I shouldn't say drawback because it's the wrong word. In Omnitrace, when you run, it needs to understand what you want to do, okay? In order for Omnitrace to understand what you want to do, it reads a configuration file. In the configuration file, you declare variables what you want to do. So when you run Omnitrace avail and categories and options, you can start seeing like Omnitrace avail does see perfecto. Show me the perfecto related variables. And you can see here some variables like that and the value and which category it is. However, we will see better description. I think it's here. So if you do here, Omnitrace avail see Omnitrace related environment variables. And then also BD, brief description, you can see each variable, something says something, okay? Text in English, so something to understand what's happening for this variable. Now, to make it clear, you don't need to know all these variables, and we'll see, I mean, depends what you want to do, of course. Sometimes, yes, you need to know many, and this is like, let's say, the learning curve to use the tool, for example. So with this command, you can see all of them, because sometimes something you don't know that exists if you don't search for it, right? And this is so, and we need to create also a configuration file. And how you create a configuration file, you do a omnitrace avail .c, a path that you want, and you call it here omnitrace.cfg. You can call it as you want. But if you want to add a description for each variable, so this one will print a list like here with the values, okay, without description. But if you want to add a description per variable, you does all, and now each variable has a description above it that says what this variable does. Okay, so this is the way to create a configuration file. Okay, this command, and you need to create it only once, right? I mean, this file can be valid for all the applications you run. Of course, if an application is different, I mean, here, for example, you say this is a PI application, right? For example, if your application is Cocos, you need to activate this, for example, right? So you have to play like that. It depends on what's your application, you activate or disable something. And you have one file, one configuration file, you can have more, but each time you need to define here which file you use. Okay, so it's important to define the file. I think if you don't define the file, it will do something default, but you will not get what you want probably. Okay, so you create the file, and then the default file is not bad basically. If you have an API application, I think you just run it. But we'll see that this Omnitrace provides functionalities that you need to change some things in the Omnitrace CFG file to be able to activate other functionalities. So let's go to dynamic instrumentation. We said that this is some overhead. Here, basically, I have already the HPC training examples on Cetonix. You can copy it from the directory I have in HackMD. And I'm saying that because I have changed something in the make file of Jacobi. So in this Jacobi, okay, you do a make, and I run it here. Here is an example for another system, and also, I mean, don't consider we don't have MBI run, and it takes 2.1 seconds. Okay, and now I run it here with Omnitrace that it does instrument dash and my binary, and takes 1 minute 45 seconds. That's like, I don't know, 40 something times overhead from the non-instrumental version. So first lesson on a profile, always on a profile, compare the before and after, right? Because I analyze something that takes so much time, the overhead will cover any other issues of your application. Now, however, we can see here, for example, that it was passing a lot of libraries, and the functions instrumented. You can see, for example, in the output, some functions instrumented, etc. And it says, I found MPI in it, and I will be enabling MPI support, and the outputs will be created. This is about the conversion, basically, of Jacobi while we run the dynamic instrumentation. It says create some file which are functions instrumented, what's excluded, etc. So in order to print the functions that basically are how to say captured during the profiling. You can do this instrument, okay? Does V for verbose simulate. Simulate means I will not run the application. I will show you just the list of what I'm going through during the profiling, okay? And the print available functions mean print the available functions that are in the Jacobi. And dependencies, of course, not only Jacobi. So I had a case that I went through 3,000 functions, dependencies, and also, operating system, STD stuff, and other stuff. And it was a nightmare to go to dynamic instrumentation. It can take a lot of time. Also, you can demand to include with -i and a single quote specific part of the code, functions of the code. Maybe you want that because the Omnitrace has some heuristics to understand what routines from the CPU point of view to instrument or not. So sometimes it can exclude whatever considers that this is not interesting to do because has a small number of instructions, this routine, for example. And it doesn't go usually by duration. It goes by, as I said, cycles, instructions, etc. of the routine. So with -i, you include, and -e, you exclude. If you want to exclude something, a routine that it captures, but it takes a lot of overhead, for example. And as it's here, you see only these two functions are shown to be instrumented because we declare here this stuff. Now, one solution to a lot of overhead, and which I always like, is binary rewrite. What does it mean, binary rewrite? Omnitrace instrument, options of Omnitrace, -o, new binary, -- your application. So I'm taking Jacobi, the original code, and I create a new one, which I call it whatever name I want, .ins. And the new binary will have instrumented functions, only the ones that they are required. And there will be the binary integrated, okay? So when you run this, you will see all the information, how many modules processed, again, similar, and it will create a new binary, okay? And default instrumentation is main function and functions of 1,000 instructions and more for CPU. To instrument the routines, for example, like 50 or more cycles, you have to add the -i50. But it will create more overhead. Okay. Now, the binary rewrite is also, I would say, mandatory if you have MPI application. The MPI, the processes behave much better with binary rewrite. Dynamic instrumentation can take a lot of time and it could also potentially crash. Now, in the Jacobi example, okay, we did so instrument -o, this is my new binary, and how I run it, srun, omnitrace run, Jacobi.heap inst, okay? So now, to run something, you use the omnitrace run, and your new binary, okay? So this one, I don't have here the time, I think. This one is like 3 seconds, for example, right? Before I had 1 minute, 28 seconds, and now it's, we can do that later, is 3 seconds. So the overhead that was like 50 times, I became, can be again 30%, let's say, right? I don't know, but because it's really small code, right? It's 2 seconds only. It became really minimal. So the one lesson is, of course, to know always how much is the overhead, because if it's significant, you shouldn't do really analysis of at least of the timeline. You can take information about how many times a routine is called, etc., but you cannot trust the time, especially. So the binary writing decreases a lot of the overhead. And yeah, I forgot to say something. When you run with Omnitrace run, whatever you run, it will create an directory omnitrace does your binary output timestamp. So if you run many experiments, always will have different timestamp, okay? So you don't worry, override something, etc. And then there are many files depending on your omnitrace.cfg. There are many files. So this one is about ROCm tracer is about the kernel's activity. And when you open this txt, let's go from the right. You can see here the percentage of the time for self, so 100% or 0, but this is not useful so much. The mean value of the time in seconds, the sum, units, metric, how many times it's called, depth. Now, here, let's see something. Okay, we see some things that we don't really care. Okay, pthread create, start, okay. Heap get device count. Okay, this is just some calls. You see here, heap memory copy, local, let's see, Jacob iteration kernel, and you see here Jacob iteration kernel. And you see it here twice, okay? And you're wondering maybe why. Some of this, especially this example, is like call stack list of the function. What does it mean? In your code, somewhere you call heap memory copy, you call this kernel, this kernel, this kernel, continue something else, you call heap event create, and then you go heap launch kernel on this and this, and heap device recognize, and you call again some other things. So especially the depth, when you are inside, is about call stack kernel. It means it's like the sequence of happens. It's not like, oh, I will see this. It happens, for example, 959 times. It's the only time that it runs. It can be running also later. And there is another configuration of CSV file to see the unique calls to all the events. Okay, so this is just for a warning. Now, when you open the Perfetto, and we'll do that, you can see something like that. So, first of all, one difference with before, I think, you see a lot of CPU frequency here. What is that? This is the actual CPU. Has it depends which machine. It has 64 cores. Okay, so you will see 64 lines of these. This can be removed, so don't worry about that. However, the frequency is called statistically, right? So it's not really accurate, but you can use little counters for more specific. Now you can see main routine, you can see API need, and you can start seeing other stuff, and you have to zoom to see more details, what happens. Now this is a trace of CPU functions, CPU metrics. And when you zoom, and again, WASD, right? You can start seeing what happens in your code, right? And what is called, as we said before, and with now zoom in stuff, and we'll go even more zoom, and now you see here the heap latch kernel from the CPU goes to the activity, and it goes at device 8 Q1, for example. And this one example had also markers, for example, like markers, right? Markers is when you have a ROCTX that you can define it yourself. Now, here also you can see something else. GPU memory usage across the time, okay? And here it doesn't decrease so much, doesn't change so much. And let me see, CPU peak memory, GPU busy. And you see here, GPU busy is almost, that's why I'm saying sometimes some results are weird, because why is that? When you see here, GPU, something starting with GPU, not GPU, when the word is GPU busy, is through ROCm SMI. ROCm SMI. ROCm SMI is statistics. So which means if your kernel is small, a chance something, high chance not to record the event. And then you lose information. And we'll show you how to use hardware counters with these accurate results. Now, GPU memory usage, again, in this example, is really low. I have seen examples that increase, decrease, etc. GPU temperature, This one should be accurate with what point? The ROCm SMI returns the GPU temperature. So it is sampling, but it's one of the main, if not only, places that we can take as user, I mean, take temperature. And so that's why you have a lot of information from here. Now, yes, this is the flow events, and also here you can choose what to show and the GPU characteristics. So I was going to the hardware counters. Okay, so how you can see the hardware counters that are available? Forget the PRN. Okay, SRAM -N1 Omnitrace avail -- all. It will print a lot of stuff, like components categories. I mean, I have never used this. It's like component alinea map and yeah, CPU clock we have used, CPU utilization, etc. Environment variables, okay, depending on what is the values, etc., the description. And the CPU hardware counters, the classic ones, right? PAPI, L1, TCM, level 1, data cache misses, and you can see what's available if it's true or false, right? So depending on the CPU, etc. And GPU hardware counters that you can see here, various names. I'm sure we don't know all of these names, okay? This output is just a snapshot, right? Now, what is here, device equals 0? It means that this counter will operate on device 0 GPU. So even if you run on 8 GPUs on the node, it will take the counters for device 0. If you want to take for all of them, I'll show you later, you have to remove this and device 0 totally and put fetch size only, and it will instrument for all the GPUs, okay? Now, there is a lot. First of all, someone can ask what counters to use. I don't have an answer to what counters. We'll have later, I think, in next slide, but even Bob explained the classic counters we use. I would say you have to understand your application and the counters, of course, and decide which one correspond more to what you need to profile. This is one benefit, if I can say benefit, of OmniPerf. OmniPerf use, I think, all of them to try to find out what's going on in your application. Of course, adds some overheads, right? But if you know, like I don't know, there's GPU busy, right? GPU busy is a percent of time GPU was busy. This is a nice metric, but it doesn't say efficient, it says busy. That's nice because maybe you don't have enough workload, so it's not busy, so don't expect performance, right? Or total wavefronts, of course you need to have enough wavefronts to stress the GPU, for example, right? I don't know, average number of GDS read or GDS write. I think there is it's not here, LDS, right? If you know that I'm writing this number of bytes and the counter shows something else, I need to investigate what's wrong to my code, right? Or to understand better my application. Personally, I would say this takes an effort to understand the counters. I'm not talking to understand everything, right? The basic things that as developer, you have the feeling that this counter will help me. So there's a huge list, and you have also in XML files this hardware counters. Now, I think you saw already this. The VLU utilization, percentage of LUs active in a wave. Low VLU is likely due to high divergence or a poorly sized grid. Now, what I like to this sentence, when a counter says low means bad, high means good, or something like that, you understand, it's just a meaning. I like because just a number means nothing. Number 50 means nothing. If I don't know that it's 50, maximum 100 or minimum 0 to understand this is average, etc., means nothing. So when I say the percentage of GPU time, vector LU instructions are processed, total kilobytes, okay, this means something as number, okay. So I no need to read all of them, but use counters that, first of all, you can understand them. What do they mean? And there is some, I wouldn't say really great documentation. I can tell you that some documentation is coming, but I don't know how soon. But it's a lot of work happening on the background. Okay. Now, percentage of GPU time the memory unit is style, right? This is something, a metric that you can understand, for example. And full list is here, okay, in this XML file. That's why I'm telling you that you use hardware counter that you understand, that you expect. For example, people use LDS, like local data set memory, to see the band conflicts or something else. Again, here, to measure something else, if you execute this command again, okay, it will ask you to verify with a yes or no to override the previous file if it's in the same directory, right? Same name, same directory. Why I'm saying that, this run, if I remember correct, this run will stack with this notice if you do this run here, because to override, to write or not. So delete it or move it or save it back up if you want to overwrite it or whatever you want to do. And how you add hardware counters, you go to this file that you created and say, I want to use this ROCm events, GPU busy for device 0, wavefronts device 0, memory unit device 0. So here I'm saying, do hardware counters only for device 0, don't do for the rest. Now, of course, depends on the code. Theoretically, this could be an okay approach if you know that the code does the same. Of course, just everybody knows, right? Between two GPUs, there is some variation. Not variation significant, but maybe the results are not exactly, the absolutely identical. However, you can try to use, because more hardware counters, more overhead, right? Etc. I don't say that this cause overhead significant, but just to keep you aware about this. So if you want to go to use hardware counters for all the GPUs, you define them like that. Okay? And now disappear all of this, and this runs for all the use GPUs. Something important, if you have reserved 8 GPUs, sometimes we do that, exclusive or something, and you run on one GPU, define that. Define by saying in this run, does GPUs equal 1? Because Omnitrace will find the 8 GPUs probably, it will give nothing. The other results will be empty, right, if you don't use them, but you will have maybe extra lines in your perfecto that you don't need, be empty. This applies especially for the CPUs also. Now, if I do a run, the Omnitrace run for Jacobi with ROCm events, like hardware events, what will happen? You will see output, and as I said before, the directory is Omnitrace, binary, output, timestamp. And then you will see JSON and TXT files with the hardware counter you use. If after the run of an application with hardware counter, you don't see the hardware counters in here in the list somewhere, then probably you didn't define, your CFG file. I don't know if it's here. Let me go a bit back. Maybe you forgot, sorry about this, but this opportunity to remind things. It's a bit back. Oh, it's too much. Sorry about this. This one. If you forget to define this, whatever counters you declare in this file will not be used, okay? Because Omnitrace doesn't know that you ask for counters. That's my tip. If you say, but that's impossible, I declare counters, why I cannot see them in my output? You forgot probably to define this variable to the correct Omnitrace. Maybe you have different Omnitrace in different directories for different applications, right? So you need to be careful on this. It's not something really bad, but just not to waste time trying to understand why it's not here. So when you see them here, you know, okay, my Omnitrace CFG file worked and everything's here, and you can see here wall clock for duration, sampling CPU, sampling GPU memory, etc. Okay, and here says sampling because these are from Rock MSMI, right? While here is device. And when we go here, now what you see here, you see device GPU busy, device. So you see here GPU busy. I think they have this is the GPU hardware counters that we defined. This is the CPU activity here, okay? The GPU activity. This is markers, RocketX. Now, something else that I was checking recently. When you define RocketX regions, it's like the region I want to know where this region I define it. I give a name, a random name, right? Step 1. In Omnitrace and RockProv, you will see the markers in the heap activity of the specific device, etc. If you use RockProv, not Omnitrace, it will be a different row, not like that, it will be called markers. So this is something different behavior between RockProv and Omnitrace. You'll see here markers, and you have only markers here, but in Omnitrace, the markers are included in the heap activity. Okay, I'm just saying that's the case. Now, as I said before, device means accurate. GPU, see GPU busy, device GPU busy. This is sampling. Okay. So, and you see here, for example, I'm just saying difference, right? This is lower, while here GPU busy remains big. And yes, indeed, here the numbers means a peak, right? Sometimes I don't get all of them because, let's say, I mean, I have asked someone, this is like 75 degrees maximum. They have told me yes, but it's sampling, so don't trust exactly the value, etc. Now, tracing multiple runs. Do you remember before in the RockProv that you had to do the wrapper, the script, and try to do all of these tricks to make it work, right? What are we doing now? We do binary writing, Omnitrace instrument, what? The Jacobi, and name it how? As you wish. This one. Dash O, Jacobi heap inst, dash your binary. And then srun dash n to Omnitrace run. In order to run, you do Omnitrace run. Instrument, Omnitrace instrument, run, Omnitrace run, dash your Jacobi, some argument. This means argument is two processes in one GPU, I think specifically. And it runs. And what happens? You see the output now. Work clock 1, work clock, sorry. Sorry. 1 and 0. Each process creates its own file. No wrapper as before RockProv, nothing. Just running the binary. This is what we're talking about. These tools are an improvement compared to RockProv. Just to be fair, RockProv is getting improved all the time, right? In the latest versions, there's a lot of improvement. And by latest, I mean, yeah, 5.4 and later, for example. And there's a new version also of RockProv. But we'll show you here how much easier it is to take data from MPI applications compared to a RockProv, right? And also you take what? To Perfetto, right? And I have Perfetto, I can call it 0 from process 0, right? And MPI 1, and you can see here, okay? Now, depending on your application again, you can see if it's of uniform, if it should be similar between them or not, for example, right? And how can we merge them, right? You do really simple. Cut Perfetto 0, Perfetto 1 to one file that you want. And then you can load it like that. Load the file, this one. You can see the differences, the different executions. You can open and you can see, for example, look here. The API reduced how much time it took in the first and second, for example, etc. Okay? So I handle Perfetto. I shouldn't say this is wrong. I shouldn't say ASCII, but you can merge traces like that and visualize. If I have a really big one that I cannot visualize, and I should add it here. I don't have it here. Let's say you have 5 gigabytes Perfetto, and I know there's some efforts to visualize big traces, but close to 2 gigabytes is a limitation. Okay, so when you run like, I don't know, 2,000 GPUs and you create a lot of data, you can 2 gigabytes is nothing basically. What you can do, you can say, I take with the command head 1,000 lines from Perfetto 0, okay, and with another set or something, I jump 100,000 lines and I take the next 100,000 lines and I make a new Perfetto. And I can visualize the thing that I extracted. 1,000 lines for the header, let's say 1,000 is too much, and 100,000 lines from after a few seconds, I can merge them, make one Perfetto, and visualize this. Perfect? No, it's not perfect, but in the case you cannot visualize, is a way to make it happen. Okay, so that's why I'm saying that I handle Perfetto like ASCII, but it's not the correct term. But I'm just saying that it's really easy to extract information. Of course, if this was extracted, don't try to check the first and the last events, right? Usually this can be broken, so check more inside. Now, statistical sampling. What I really like, in default, use sampling 0 means I use Jacobi and I have this one information, right? You can zoom, see the events. Now, if I say, please do sampling, this is sampling on the CPU and frequency 100, which means 100 samples per second, I can extract all the call stack. So here, maybe say, this one from where is coming the code, right? I don't remember exactly. And you go to see the call stack. And you can see, sometimes, of course, you can see same event repeating. This is not your calls. Your call stop, maybe heap mem set is what you did, but some other stuff is what happened in the background, right? And then you go to Zoom and you start seeing, okay, what happens. Also, if you click one of them, let's say the heap API name, all of the same calls of the same level will be highlighted to know what happened, okay? And of course there is, thread 0s is sampling data annotated with S. So you can see the thread, I don't know if it's here. I cannot see it here, is crop, that this is sampling. However, you can see the call stack, right? And you can go in level and see what happens. Or if something seems wrong. This is something that I really like, and many people have found it really important. And this is something you cannot do with just RockProf, okay? That's why we say that these tools are an improvement compared to RockProf. Now, other features. Kernel durations. As I said before, when you do cut the wall clock of the output, but if you don't see a wall clock in your output, then you go to the Omnitrace CFG file and use the time memory. Sorry, team memory. Team memory. That's called. True, because this will start activating all of these functions for wall clock. And this is what I was saying before, the wall clock per call stack, right? We call this, and then it's called this, and then it's called this, and it goes level inside, level inside, level inside, and you see here the same, the time, the duration, etc. And the text file is for quick reference, and there's a JSON output also, right? With TXT, it's created a JSON file, and there is a script. There's a script that you can extract information from there, but I haven't really used it a lot. So this by default, when you activate the team memory here, you have this wall clock, and you can see all of this. Now, this is a bit strange because it's a call stack, but you can identify where I am close to the code, right? Because if you are in a loop, then you call this is the routine of the loop, for example, you can see it. Although here it's not a loop because it's called once, for example, right? But you can understand the concept. Now, flat profile, okay, I go back, kernel durations. I go to flat profile. You need to add this flat profile to true. I think this one, I'm not sure. Before it was not in the Omnitrace CFG. I think now it is. Or you can add new, not new from your side, new that it's not included in the Omnitrace.cfg yourself, right? And the flat profile does exactly what you assume it does, right? You can see everything only once. How many times it's called? You will not see again this kernel, this MPI, this whatever. And also, you see the units, right? The minimum value, maximum value, variation, standard deviation, and of course all are 100% because they are called only there. They don't call it in other places, okay? So the flat profile is useful for what? To understand in which kernel to focus, which one takes more time, right? Of course, with RockProf, if you do RockProf stats, you can easily see which kernel, right? However, with flat profile and MPI, you can take one file per MPI process, right? So you can see, and across the MPI processes, how varies something specific. Now, let me say something that I forgot to say. Sorry for MPI. Here, I merged these two, right? Someone told me that there is a limitation around 10 processes to merge. I'm not sure why. Yeah, it depends on the size of the files also. But this is not a nice way to visualize 500 processes, right? This is an example to visualize small number of processes. For large number, we don't have something yet to visualize like that. I see a question. Is a question, Pascal?
Yeah. So it's just with the flat profile, because it's something I've found before, right? That the flat profile with like a min, max, a variance, a standard deviation. If you have something that's quite an unusual distribution, so I've had stuff where normally like it's not a Gaussian distribution, so the mean, the max, you'd rather have medians and percentiles to understand what's going on, because the max might be very large, the mean might be very small, and there's like not a simple sampling. So I don't know if it's anything that, because it's not often done, but is there a way to configure Omnitrace to generate a flat profile where the stats are not just sum, mean, min, max, and let's say standard deviation, but you could provide percentiles? Is this something that it was a feature request I'd ask for actually for flat profiles, because things are not necessarily like simple Gaussian distributions with like the mean meaning something that's obvious and the standard deviation also meaning something that's obvious.
I don't think we'll have something like that, but I would propose you to create an issue about this.
Yeah, so I was gonna do it. I was just wondering if you knew in the background if anybody's put in this feature request.
You can see in the issues, you can see if someone, we can search the issues and see if someone did that.
Okay.
But I'm not aware of a request this moment, something like that.
Okay, cool. I wasn't expecting it, but thanks.
Yeah, but please create an issue. I mean, I'm not saying that we solve next day, but if they like the idea, they will put it in to act.
Okay. Cool.
Now, user API. So you have, let's say, you have a huge code and you want to start trace and stop trace specific areas to avoid big traces, right? Or they have also here start thread trace or stop thread trace or user-defined regions, for example, right? And there are plenty of this, and here is a user API, okay? This one you understand is like, if you have a huge trace and you are not interested to trace everything because I want to focus on a specific area and the trace is too huge, you can integrate the API calls and decrease control the segmentation basically and decrease the size of the trace. It can be really useful in many cases, I would say. Again, it depends on what you are doing. Now, about OpenMP. OpenMP is for CPU, right? I have tried and I failed Yes, I failed, I think, to profile OpenAP offloading with Omnitrace. Now, the developer had told me that there is some support, but for some reasons it failed, but he hasn't tested significant. So in the Omnitrace source code, there is some examples, OpenAP, and just say here, just compile it, you just define how many OpenAP threads, and you run OpenAP LU. Here you have to create, this is a non-instrumented, right? And here you have to create a new instrumented binary. So you do Omnitrace instrument, house called my new binary, OpenAP LU inst, that's my binary, okay? So now the new is called this one, the my new binary, and how I execute it is run one API process, 4 threads, Omnitrace run dash OpenAP LU inst. And then you have the whole clock txt, and you can see for, okay, 1, 2, 3, 4, one API and the rest 3 threads with data about the time, how many times counted, the same information, right, about the time. So you can instrument and see the OpenAP for the CPU. Again, now I'm just wondering how many people have significant. How many people have a significant OpenAP CPU code that they want to? Maybe they are that they want to keep it on the CPU. They don't care to offload it for specific reasons that are not so efficient on the GPU or something. So in this case, you want to have this information how the CPU code performs also, right? That's why this tool is comprehensive, it's CPU and GPU. And of course, as I said, for threads, again, you have Perfetto, and sorry, I had to zoom more, but and here's the 4 processes, right? And you can visualize the OpenAP stuff, etc. So yes, and here you can see the different threads. Python was something. Python is for many people interesting. As you know, Python now with ML workload, it gets crazy. So I haven't tested this. I didn't have time to test this on Cetonix. So the Omnitrace Python package installed in where you installed Omnitrace is here. Okay, normally you have to set up the environment, Python, all of this stuff in the Python path. And we use Fibonacci example again from Omnitrace source code, examples Python source. And now you execute as Omnitrace Python and the Python file. And the difference, one of the main difference, is now the directory is called Omnitrace source output. I don't know why it's called source and not, because probably not the, I don't know, the file name, but it doesn't matter. So now it's this output, timestamp, and have the whole clock. And the Python documentation is also here. So we have Fibonacci, right? And most of people who know how it works Fibonacci, and when you open the whole clock, now you can start seeing the run and the Fibonacci hash code and the counters, right? How many times, and the depth increase, who called whom, and the same stuff about the times, okay? And here you can see all the 4 differences of the self percentage. So, okay, so it's quite interesting to be able to see Python visualization. I think we didn't have, for sure, I don't think RockProf does this thing. And it's really happy because some people use Python a lot. Although some I'm not expert on ML, but some frameworks have their own profiling stuff. But it's nice to have something extra. And of course, you can visualize, right? Perfetto again, and see here the Fibonacci is a bit a mess, but you can start zooming to see more information. Now, Cocos, I had this example because I was happy that it does work. Basically, we had the Cocos binary, basically. And yes, this is also, I have to remember now, or binary writing or dynamic segmentation, I don't remember now. I activate it here in the CFG file, only this line. I run it, and I see this file in the output directory, and start seeing information about this is Cocos memory, right? And again, whatever Cocos does, and how many megabytes of memory use, or I think here's a minimum. Yeah, I don't have here the headers of this. And for me, was impressive that I could instrument Cocos like that without doing basically anything. And basically, when you visualize with Perfetto, right, with sampling enabled to see the call stack, you can see the call stack, right? Because this is some hydro codes that goes inside and calls other stuff and heap events. And the users were really happy because first time they saw this kind of instrumentation. This was live during a hackathon. And also, I used the same code also for the roofline also that we'll see tomorrow. So this way, we're really happy that we see that Cocos just work like that, right? Now, other executables, there is Omnitrace sample. Honestly, I don't use it so much. This is to do as the word says sampling. Initially, I was not a fan of it because I had to define everything as options. What does it mean here? Profile, host to host and device, data transfers, exclude everything but keep Rock MSMI, Rock Tracer, Rock Profiler, Rock TX, and run Jacobi. So this is something that I don't find it so user-friendly to remember all the options. Of course, you can get in the script, etc. But with sampling, you lose information, right? You don't expect that everything is captured, but here, because we do -I, the GPU stuff will be included, the CPU maybe not. Omnitrace causal invokes causal profiling, and unfortunately, I don't have yet something to talk about it. It's really interesting, but needs some time. And the critical trace, I think this needs more development. This is about, I have a lot of code, I have a huge application, but I want to know the critical trace because I'm not the developer. Maybe to know exactly which path follow the application. And for these executables, the current documentation again is here. Now, tips and tricks. I have to say something before I start the slide. I was using the Omnitrace and OmniPerf for some time, and I had a lot of problems. I could crash the tools really easy, but when I say really easy, not with toy cases. So I was helping to understand an application from KTH in Sweden. Nico is for the family of NEC 5000 codes. And the funny thing is that this code, a case that we were using, and I will mention tomorrow, had 6.7 million dispatches of kernel. And this was not mistake, this was not non-optimized. This code runs efficient in 80% of the LUMI, and it was really good. And I started to have problems because the tools, when they implement the tools, they have some specific applications that work, and maybe they don't stress them so much. So through stressing, we had a win-win because we learn how the tool maybe is not so good and improve it. And at the same moment, the user can use a tool with their code. Now, so my Perfetto timeline seems weird. How can I check the clock skew? What I mean here, I had from CPU calling heap large kernel, and the kernel of the GPU of the timeline was before the heap large kernel from the CPU. So a kernel started on the GPU before it was called from the CPU. So there was some clock skew that when you define Omnitrace verbose equal 1 or higher this can be or in the CFG file or the submission file, I think, then they will print the timestamp skew to know what to expect. Okay. Second, I said 6.57 million dispatches of kernel. It was never finishing. I was in the last step of Omnitrace, and I couldn't finish really the execution. The Omnitrace was stacking forever because has a mapping RockMSMI samples to kernel and map which kernel it is. So imagine 6.7 million. So when I did that, I disabled this mapping and finished fast. However, now, because I gave the code to the developers that reproduced the problem, they fixed that. So this is not required, but I have it here just in case. And this is for me, again, a win-win because we learn where our tool is not good and we improve it, right? That's the point. What's the best way to profile multi-process runs? Use binary write. If it's multi-process, do a binary writing. Instrument the binary first and run the instrumented binary. You will see the examples. If you run Jacobi dynamic instrumentation, it will take forever and maybe it will crash without binary writing. Okay, so that's why we do binary writing to be much more efficient, and it is important. Now, if you are doing binary writing and you do not get information about kernels, not kernels, set this one in the environment and Omnitrace use RockTrace on in the CFG file. So again, we had some stress situation that we were bypassing the libomnitrace.so by the application and how to define it here to take information about kernels. Some of these things you will never need it, but I like to have them because it's a slide that if I see a problem related, I can go and test if a solution is here. Now, the same code was hacking different points. It was hacking 3%, 50%, 97%. It was making me a bit crazy why it hangs. I don't understand. And the developer told me, okay, activate this in the environment, and this changes how heap runtime is notified when GPU kernel is complete. So this is something different communication to HSA layer, but this helped to not have this problem again. Okay, so again, this is something that I couldn't know without someone to have used the HSA layer, etc. My Perfecto trace is too big. Can I decrease it? As I said, 2 GB is the limit. I mean, above 1.5, I would be worried. Of course, it depends what you visualize also, right? Maybe you have a server, but it's not about server. It's about the Chrome or the browser limitations, I would say. Because I have tried it in the big systems also. And again, the limit is the same, even if you have a 64 GB memory. So if the Perfecto trace is big, since version 1.7.3 is quite old now, declare Omnitrace Perfecto annotations to false in the CFG file, and they will exclude a lot of annotations that we don't need. And we had an example that from 2 GB went down to 500 MB. That was significant. Doesn't mean that happens for all the applications. For this application, it happened. Now, something else that I added now, because many people ask me, I want to remove the many rows of CPU frequency lines from the Perfecto trace. Go to the Omnitrace and declare use process, not sampling, use process sampling equal false. What is that? Let me go back again. Yes, it is here. Sorry, it's here, but not so good. Here you will take 64 lines CPU frequency for 64 cores. All of this will disappear. It's really ugly to have them if you don't use them, and usually we don't use them so much. Okay, so this is for me is a slide of tips and tricks to remember how to do something or how to fix something. Now, the summary. Omnitrace is a powerful tool to understand CPU and GPU activity, idea for initial look at how an application runs. Remember, this is timeline, so you can see the iterations, you can see how it performs, you can see API. Now, something else, okay, interesting, something else and I'll go back as I remember what happens in the hackathons, and maybe it's useful. Someone told me I cannot see MPI in my Omnitrace. And I told them that's difficult because, because MPI is by default when you instrument MPI application. But they were calling MPI from a layer, not from the main, but from different in the call stack. So if you don't activate the call stack here, you cannot see MPI. So you can see MPI, I don't know, something like here was my my pointer, for example. But if it's not called from the main and you have to call the call stack, you will not see it here on the top, right? Because it's not here actually. You have to activate the call stack. And this happened basically on the, I think on the Gromax also, someone was profiling. Yeah, this is also, yeah, maybe I should add it also in the tips and tricks also, this one. Yeah, so this is what we learn while we work with the users and various hackathons. Leverage several other tools and combines their data in comprehensive output file. There are plenty of tools, I mean, the uProf, FrogProf, and other stuff. Easy to visualize traces in Perfetto. I would say easy if the size is correct, or you can extract at least, but it's not the best solution. But you know, when you can extract a big trace to smaller pieces, you can do a script and you can really split the big trace to smaller ones, right? Not do it manually. Do a script to split the trace to smaller and visualize many times the different time zones, okay? Timelines as you wish. Include several features, dynamic segmentation, either at runtime or using binary write, statistical sampling, process sampling, causal profiling, critical path tracing. So I'm sad that I'm not talking about causal profiling, but I didn't have time. So this one with simple words, it takes in progress points, and by point I mean either API call or your OpenAPI call or maybe something else, or end-to-end. End-to-end is all the application, and we run many times. And with some not counters, you define what if this function or this range of code, line 100 to 110, can run 20% faster, for example. Or a random one, it tries to place with a variation and to tell you what you will achieve or not achieve, for example.